We're in Unit 10, Notes 5, and today we are going to be finding the area inside of a polar curve. With rectangular equations in rectangular form, it was useful when we were finding the area under a curve. It was useful to use rectangles to get started with our process that we used to for finding the exact area. And when we did that, we used either a right or a left Riemann sum, but we were using rectangles, right? And we approximated the area underneath this curve with rectangles, and some of the rectangles went above the curve, some below the curve. That's depending on whether we had a right or a left Riemann sum, and so forth. So we used rectangles. And the area of a rectangle is length times width, or base times height, and each rectangle had length or base length change in x, delta x, and each height was the function value, right? And so that is base times height, or length times width, however you want to talk about it. And we added those all up, and then we let the number of rectangles go to infinity, and we got the integral from a to b, whatever our a and b are, of f of x dx. And that is the area under a rectangular curve. Well, now we are in polars, and using rectangles to start this process of finding the area inside this is not going to be efficient for us. Okay, where's your rectangle going to go? Right here. And depending on the polar curve, right, depending on your polar curve, rectangles might not be very efficient at all, right? So we're not going to use rectangles. So our area equation is not going to look like this. And that's the first, foremost important thing to know. When you're in polar form, this is not the area inside that curve, okay? When you're in polar form, you don't use rectangles. When you're in polar form, we're going to use sectors instead of rectangles. A sector is a part of a circle, okay? So if we take a look at this, if this is one radius of a sector, then the part of the little piece, the little sector, would look something like that. And it's hard to see, but it would not be lying directly on this curve, because the way I drew this curve, it's not a circle. So it will, since this is going to be longer than this sector is going to come outside. It's going to be an overestimate right there, okay? The next sector would be going from here. It too would be over that curve like that. And the next sector would be here. It too would be over the curve, etc. And then we would keep on finding all of these sectors. And we can find the area of a sector. As we get over here, it's going to be more obvious that it is an overestimate. And so forth. And we would keep going around all the way around, right? So we would be going from theta equals 0, in this case, all the way to theta equals 2 pi, right? To find the area inside this whole thing. So we need to know what the area of one of these little sectors is. So let's think about that. If you have a sector, if you have a circle, the area of that circle is pi r squared. That's the area of the whole circle. Well, we don't have the whole circle. We just have a little piece of that circle. We have a little sector, right? So we're going to set up a little proportion. The area of this sector I'm not going to call this A, but we know the area of that whole circle is pi r squared. The area of this sector I'm going to call A. Okay. A is to the entire area circle as this theta is to 2 pi, because 2 pi would be all the way around here, right? So the area of the sector would be pi r squared theta divided by 2 pi. So the area of that sector is 1/2 r squared theta. That is the area of a sector, of one sector. Okay? So the area of one sector is 1/2 r squared theta, right? Now, our thetas are going to be tiny, right? Our thetas are going to be teeny tiny, little slivers. Just like up here, these were little delta x's. These are going to be delta thetas. So each little angle is a change in theta. And we're going to add up all of the areas of all the sectors, and we're going to take the limit as theta goes to 0, which is the number of sectors goes to infinity. That gives us the integral from a to b, in this case 0 to 2 pi, of 1/2 r squared d theta. And that is the area inside a polar curve. Area inside a polar curve. Okay? So I didn't go through all of that detail in your notes packet, but that's how we get to these equations. Sometimes we pull out that 1/2. Alrighty? Okay. Let's look at an example. The graph of the polar curve, r is equal to 2 plus 2 cosine theta, is shown on the right. Find the interior area. Interior area. So here's my mind. Here's what I have in my mind. If I start at theta is 0, the first little sector will be here, and then here, and then here, and then we're going to go all the way around. When we get to here, we've gone from 0 to pi over 2, right? But I need to keep on going because I have not filled in this whole polar curve yet. So if I keep on going, what is this theta? When I get back to the origin, that theta is going to be pi, and then we keep on going all the way around to 2 pi. Back when you were doing your polar refresher, I said we need to know the theta values, a set of theta values that form one complete graph. This is when. Right here. This is when we need that. So the area is going to be from 0 to 2 pi of 1/2 r squared d theta. You got to know that formula. 1/2 r squared d theta. And we can put that into our calculator. Let me get my calculator going here. We could do this by hand, but there's no need to if we have a calculator in our hands, right? So I'm going to have math 9, 0 to 2 pi, 1/2 r squared, where r is 2 plus 2 cosine theta. Make sure you get that in there accurately. D theta. I'm just in function mode. I'm always in function mode for these. And we get 18.8495 ... and you need to show me at least 3 decimal places. So 18.849 will work, or 18.850 would work because we can round that 9 to a 10. Okay? All right. It is important to note on this, we used 0 to 2 pi because I knew that that would work. We didn't have to use 0 to 2 pi. We could have started over here at pi and gone from pi to 3 pi. And that would have worked as well. If you put in if I, instead of going 0 to 2 pi here, if I go pi to 3 pi, that's the same interval, right? It's the same length of interval. So that gives me the exact same answer. I could have started at pi over 2 and went to 5 pi over 2. And that would have given me the same value as well. Same value, okay? So as long as this distance, the delta theta is 2 pi, we're going to get the correct answer here. So there's not just one integral that will give you the correct area on these, on any of these, okay? I could have also, and I would have done this if I was doing, I maybe would have done this if I had to do this integral by hand. If I had to do this by hand, do you notice some symmetry here? From the area from 0 to pi is the same as the area from pi to 2 pi. So we could have gone from 0 to pi, we could have gone from 0 to pi and doubled it. And that would have worked as well. Could have gone from pi to 2 pi and doubled that. Okay? So I'm saying all of these, you guys, because on a multiple choice question, the question might read, which integral gives the correct area? So you need to have some options in your back pocket to pull out in case the one that you would use isn't one of the choices given. All right, let's take a look at number 2. The graph of the polar curve r is equal to 8 sine of 3 theta is shown on the right. Find the interior area. So this is a rose with 3 petals. And for a rose with 3 petals, it's an odd number of petals. What theta values form a complete graph? Well, for an odd number of petals, 0 to pi form a complete graph. It's something that you need to know. We talked about it when we did our polar refresher in December. So got to know that. Odd number of petals, 0 to pi. Okay? You don't want to be messing with your calculator trying to figure out what theta values form a complete graph. Know that. Know this. Odd number of petals, 0 to pi. All of our other known things, 0 to 2 pi. Okay? All right, so if we want to know the interior area of this, we will just have the integral from 0 to pi of 1/2 r squared d theta, where r is 8 sine 3 theta. So math 9, 0 to pi, 1/2 r squared, 8 sine 3 theta squared, make sure you get your parentheses correct, 50.265. Okay? All right, what would be some options for this? Well, instead of going 0 to pi, we could have done any range of values whose difference is pi. So we could have done pi over 2 to 3 pi over 2. That would have worked. Okay? I see some symmetry here. I could have done 0 to pi over 3 and tripled it. Same thing, right? Could have done that. We could have done, so as long as we're tripling it, then the distance between these two theta values needs to just be a pi over 3. So it could have done negative pi over 6 to positive pi over 6. That's a difference of pi over 3, right? That would get me the same thing. So lots of options there. I've seen AP, they usually give the most obvious one when they're asking which integral gives the area. But it's good to know all of those options. Okay, the graph of the polar curve, r is equal to 3 cosine of 4 theta is shown. Find the area of one loop. So this is a rose with 8 petals, right? We only want to find the area of one loop. So in class I would usually ask for how could we find the area of one loop? And usually students will say find the area of the whole thing and divide it by 8 because there are 8 loops. And I'd say yes, that'll work. So the area of the whole thing would be, so integral 1/2 r squared d theta. That's the area of the whole thing as long as we get the boundaries correct. So for an even number of petals, we do need 0 to 2 pi. So 0 to 2 pi. And then that would give us the whole flower, the whole rose, and we want 1/8 of that. So in my calculator, 1/8, math 9, 0 to 2 pi, 0.5 r squared 3 cosine of 4 theta. Oops. Okay, so there's that. So I got 1.767 is the only possible answer here, like that. All right. So how else could we have done this? Well, we could have gone from pi to 3 pi with the 1/8 out in front, or 2 pi to 4 pi, or 4 pi to 6 pi. As long as the 1/8 is out there, all we have to do is separate this by 2 pi. All right, what could we have done to get to not use the 1/8 out in front? Well, if we don't have the 1/8 out in front, then I need for my theta values to be cut into eighths. So 0 divided by 8 is still 0. 2 pi divided by 8 is pi over 4, right? Will that give me the correct answer? Yep, it sure does. So we've just cut our integral values into eighth by 1/8. Okay? Multiply them both by 1/8. Or could have done negative pi over 8 to pi over 8. So as long as those theta values differ by 1/4, our answer will be correct. And I will tell you that if this was which integral gives the area, that very well might be the one that they use. Okay, and I'll show you why. If we want another way to think about this, is I want the theta values, I want to algebraically find the theta values that form one loop. So right here, you'll agree that r is 0 right there. Right here, r is 0. So when r is 0, and I come out and come around back to 0, if I have 2 consecutive zeros, I should get the area of one loop. So if I take r and set it equal to 0 and find 2 consecutive theta values, I can use those in my integral to find the area. Okay? And I know right now you're probably thinking, I don't even need to pay attention to her right now because I'm not going to do it like that. You need to know this process. Maybe not for this particular problem, but you're going to need to know this process on other problems. So, when you set r equal to 0, you're finding the theta values where your curve is at the origin. Okay? You will need this for problems. Okay? So you're going to need to know how to solve an equation like this. So 3 cosine of 4 theta is 0 when 4 theta, that angle, is equal to, when is cosine 0? Well, cosine is 0 at all of the pi over 2's. Pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, etc. Okay? I only need 2 consecutive values, so that's why I'm only writing 2 down. Divide both sides by 4, which is the same as multiplying both sides by 1/4. And theta is pi over 8, to 3 pi over 8. So our area would be pi over 8 to 3 pi over 8, 1/2 r squared d theta. And that gives us back the same number. Alrighty? Okie doke. Let's do another one. So then we get some graphs, some equations and graphs of figures that we are not familiar with. So up until now we had like this limacon without a loop, a cardioid, and then a couple of roses. We are familiar with these. We know the theta values. We should know the theta values that form a complete graph on these. Now let's look at some where we're not familiar with these, because they can make up very interesting polar equations for us to use. And they do make up very interesting polar equations for us to use. All right, so this shown is the graph of theta plus cosine theta. That is not one of our known things. Okay, theta plus cosine theta. And it says that it is shown on the right for pi to 2 pi. Now first of all, let's look at this. When theta is pi, cosine of pi is -1. Pi plus -1 would be pi minus 1, so 2.14159, blah, blah, blah. That's what that point is right there. So that's when theta is pi. As theta moves towards 2 pi, it makes sense that the curve is going to look like this, or that the curve is going to be where I see it, namely in quadrants 3 and 4, right? We want to find the area between the curve and the x-axis. Area between the curve and the x-axis. So I'm going to start my theta at pi and go until I get to 2 pi. And that should give me the area. Okay? So integral pi to 2 pi 1/2 r squared d theta should give me the answer, right? So math 9, pi to 2 pi, 0.5 r squared, so theta plus cosine theta squared d theta, so 38.959 is that area. Okay? Now, a couple things. Notice that, and I've realized now I haven't been mentioning this, but your theta values have to go, if you're doing this, they're going to go from the lower theta value to the higher theta value. We're not going from 2 pi to pi. If we did, we would get a negative number here. Okay? So, lower to higher. So our little little sectors are starting, the little sectors are only moving counterclockwise. Each sector is, moving counterclockwise from the previous one. So only go counterclockwise. That's going to be more important. You're going to see why I stress that tomorrow when we're doing area between curves. But only go counterclockwise. If you get a negative number when you're doing this, it means you've done something wrong. If you can see the area, it's not going to be negative. Okay? All right, number 5. Find the area of the inner loop of r is equal to 2 plus 4 sine theta, the inner loop, whose graph is shown for 0 to 2 pi. All right, well, this is 0 to 2 pi, right? I don't want the entire inner area. I only want this inner area. So I need to find out what theta values these are, because my little sectors are going to look like that. Okay? Well, the sectors are actually going to look like that, but you know what I mean. Okay? So, I want to find the theta values where r is 0, because when r is 0, that's going to be my theta values that I start and end this little loop on. So this is one of those where you're going to have to know how to solve these equations. So I'm taking r and I am setting r equal to 0 and solving it for theta. So sine of theta will be, I'm subtracting 2, then dividing by 4. So sine of theta is negative 1/2. So theta is, in quadrants 3 and 4, the pi over 6 angles, so 7 pi over 6 and 11 pi over 6. Those are the theta values that bound my inner loop. Okay? Let's think about this. When theta is 0, sine of 0 is 0, and we're at 2. So right here is where we start. And remember, we only go counterclockwise, so we're starting off going this way. And then we go all the way around until we get to 7 pi over 6, and then this little inner loop is formed. It ends when we get to 11 pi over 6, and then we keep on, the theta keeps on going and gets that little sliver to get to 2 pi from 11 pi over 6. So our area of this inner loop is going to be the integral from 7 pi over 6 to 11 pi over 6, 1/2 r squared d theta Math 9, 7 pi over 6 to 11 pi over 6, 1/2 parentheses. Make sure you get that in right. And I get a little 2.174. Okay? All right. Before we leave this little graph, let me ask you a question. What if we have 0 to pi of 1/2 r squared d theta? What would that give us? What would 0 to pi give us? Okay. Well, 0 starts right here. We already talked about that. There's where 0 is. If we're going to go from 0 to pi, the next little arc is going to be like, the first arc will be here, the next arc will be here. Okay. And then we're keeping on going, right? We're keeping on going. What area are we getting from 0 to pi? We've gone from 0 to pi over 2, and then we keep on going. Right? I forgot to get that one. Go ahead and we'd end there. So what area did that give us? That gave us this entire top, including the inner loop, right? It gave us the whole thing, including the inner loop. So what would 0 to 2 pi give us? Well, 0 to pi is what I have in green there. And then we come and get this sliver. And then we're going inside and grabbing that inner loop, which we already got going around the first time. And then we get this other piece. So this, from 0 to 2 pi, would give us the entire area plus an additional inner loop area. So 0 to 2 pi gives us way more than we want. Okay? It gives us 2.174 more than we want. So we have to keep that in mind. All right. Number 6. The graph of r is equal to theta sine of 2 theta is shown on the right for 0 to 2 pi. All right. Find the sum of the areas of the loops in quadrants 1 and 2. I can see the loops in quadrants 1 and 2, so I want to find the sum of these. That's what I want to find. So I need to find the theta values that bound those. Question: do you think it's 0 to pi? And I would let kids in class answer and give me their thoughts on that. Do you think it's 0 to pi? And if you don't think it's 0 to pi, why not? So these are the kinds of questions. We would spend some time on that, just talking about this in class. But we're not in class, so you just get to listen to me talk. All right, first of all, when these graphs are formed, chances are, and depending on what the equation looks like, but chances are they're going to be smooth. There's not going to be any jerky motions. There's not going to be any cusps. So when theta is 0, r is 0. So I know we're starting at the origin. As theta starts to move, as theta starts to go from 0 to 2 pi, as theta starts to move, this is positive, and sine is positive because I know what sine looks like. So as we move, we're going to form this little loop right here. We're going to form that little loop. But as we form that little loop, I'm not going to stop here and then bounce and come out and get this big loop. It's not going to be how it operates. I'm going to form that little loop, and then it's going to smoothly come. Chances are, I'm thinking it's going to come over here and get that loop, which means from 0 to pi over 2, I get this tiny loop. From pi over 2 to pi, I'm actually down here with a negative r value. I'm thinking that that's where r is negative because sine in that segment, sine of those angles will be negative. Because sine can be negative, right? And it is. Sine is going to be negative from 0 to 2 pi at places. So that's where r is negative, and theta is from pi over 2 to pi. And then when we get to pi, it's going to come over here and get this piece, and then it's going to come and get that piece. Look at how these loops grow in size. That's another indicator of where this is located, the theta values that form it and when. This is the smallest loop. That's when theta is the smallest it can be. As theta grows, this is going to make this whole thing grow, right? So as theta grows, each loop is going to grow. The next loop would be back in here, and it would be bigger than this loop. And then it would come over here, and it would be a bigger loop, and a bigger loop, and a bigger loop. It would be a very nice, fun graph to look at. So you should go play with that if you want. But my thought is, for the area that I want, I'm thinking I need to use 0 to pi over 2 and then 3 pi over 2 to 2 pi. I'm thinking I need to use the theta values from 0 to pi over 2 and 3 pi over 2 to 2 pi. But let's confirm that. Let's confirm that by doing a sine chart on R. Let's confirm that by doing a sine chart on R. Okay? So theta sine of 2 theta, setting that equal to 0. Theta might be 0, or 2 theta might be 0, pi, 2 pi, 3 pi, 4 pi, etc., etc., etc. Okay? Multiply both sides by 1/2, and theta is 0, pi over 2, pi, 3 pi over 2, 2 pi, etc. Right? I only went to 2 pi because I know I'm stopping at 2 pi. So this 0 is already here, so these are my theta values, where R is 0. 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay? And I want to sine chart R because I want to know where R is negative. So I'm trying to find out, where is R negative, where is R positive? Where I want to confirm what I'm thinking here. So when theta is between 0 and pi over 2, like pi over 4, when theta is pi over 4, positive, sine of pi over 2 is positive, so positive times positive is positive. So it doesn't shock me that when theta is between 0 and pi over 2, R is positive. Okay? All right. So that's going to form that right there. So I know I need the integral 0 to pi over 2 of 1/2 r squared d theta. I know that's going to be part of the area that I want to find. And then I also know that I know enough about sine to know that it does alternate signs around its zeros. So I know this will be negative, this will be positive, and this will be negative. Okay? Now, that means when theta is between pi over 2 and pi, when theta is between pi over 2 and pi, R is negative, so it's going to show over here in the fourth quadrant. So when theta is here, the graph is going to be seen here. And I don't want that, so I'm not going to use from pi over 2 to pi. From pi to 3 pi over 2, where R is positive again. So from pi to 3 pi over 2, the graph will be seen from pi to pi, over here in the third quadrant. Then, when theta is between 3 pi over 2 and 2 pi, R is negative, so the graph will be seen flipped through the origin in quadrant 2. And that's one of the ones I wanted. So I'm going to be adding 3 pi over 2 to 2 pi of 1/2 r squared d theta. Come to our calculator, and we have math 9, 0 to pi over 2, 1/2 r squared, theta sine 2 theta, d theta, plus math 9, 3 pi over 2 to 2 pi, 1/2 parentheses theta sine 2 theta squared d theta. So I got 12.175. Alrighty. And that is area inside of a polar curve.